Hello friends, I am Dr. Aparna Dhote, Assistant Professor, Nilkantraw Shinde Science and Arts College, Bhadravati. Today we are going to know about NMR spectroscopy. So, first, what is spectroscopy? Spectroscopy is nothing but which gives information about the number and types of atoms in a molecules. Now, in spectroscopy, there is nuclear magnetic resonance spectroscopy, that is NMR. What is it? The nuclear magnetic resonance spectroscopy is a powerful analytical technique used to characterize molecules by identifying hydrogen carbon frameworks within the molecule, and again it is used in quality control and research for determining the content and purity of a sample as well as its molecular structure. So see, the electromagnetic spectrum, that is radio frequency, microwave, infrared, visible, ultraviolet, X-ray and gamma rays. Now when we study the NMR, in which range the NMR is studied? The NMR is studied at radio frequency, and the frequency region is 4 to 900 megahertz by the nuclei of the atom. In NMR spectroscopy, the solvents used are acetonitrile, benzene, chloroform, dimethyl sulfur oxide and many more. But in NMR spectroscopy, the tetramethylsilane is used as a reference solvent. Why it is used? Number one, because it is highly volatile. It can be easily evaporated, which is convenient for recovery of sample analyzed by NMR spectroscopy. And again, the most important is TMS has 12 hydrogen atoms, even though it gives only one spectrum, because all the hydrogen atoms in TMS are equivalent. That's why TMS is used as a reference solvent in NMR spectroscopy. See classical view of NMR as compared to quantum view. Now, instrumentation of NMR. In NMR contains sample tube, magnet controller, detector, RF transmitter and gamma rays. Now when we study the NMR, in which range the NMR is studied? The NMR is studied at radio frequency, and the frequency region is 4 to 900 megahertz by the nuclei of the system. The sample is placed in a magnetic field and the NMR signal is produced by the excitation of nuclear sample with radio waves into nuclear magnetic resonance, which is detected with sensitive radio receivers. The intramolecular magnetic field around an atom in a molecule changes the resonant frequency, thus giving access to details of electronic structure of a molecule and its individual functional groups. See principle of NMR. Now when the nucleus with an odd atomic number, what? Odd atomic number or odd mass number has a nuclear spin, the splitting charge nucleus generates a magnetic field. That magnetic field that splitting acts as a bar magnet. The principle of NMR behind it that every nuclei have spin and all nuclei are electrically charged, but when the external field is applied, the energy is transferred from higher to lower or lower to higher energy level. The energy transfer takes place at a wavelength that corresponds to radio frequencies, and when the spin returns to the base level, that is from higher to lower, the energy is emitted at the same frequency. The signal that matches this transfer is measured in many ways and proceed in order to yield an NMR spectrum for the nucleus. See the spin of nucleus. The nucleus are electrically charged and many have spin, and that causes them to behave as like a magnet. Now see the energy gap between lower energy level to the higher energy level. The most important is NMR is precession. Precessional motion. As the protons behaving a spinning magnet, it can align itself either or opposed to an external magnetic field. It also moves a characteristic way under the influence of external magnet. Consider the spinning top. The top has a spinning motion around its nucleus. It also performs a lower valve-like motion in which the spinning axis of top moves slowly around the vertical, and this is called precessional motion, and the top is said to be precessing around the vertical axis of the gravitational force of the earth. The precessional motion is seen in the diagram, that is top, then nucleus is spinning, and see the precessional. Precessional frequency. The precessional frequency of the nucleus is directly proportional to the strength of external field and also depend on the nature of the nuclear magnet. So, according to landmark precessional theory, omega equal to gamma H0, where gamma is the gyrometric ratio, equal to intrinsic magnetic dipole moment to spin angular momentum. Now, gamma equal to 2 pi v, therefore 2 pi v equal to gamma H0, and therefore V proportional to H0, that is applied magnetic field. The most important factor in NMR is chemical shift. The precise resonant frequency of the energy transition is dependent on the effective magnetic field at the nucleus. The field is affected by electron shielding, which is in turn dependent on the chemical environment. In general, what happened? The more electronegative the nucleus is, the higher the resonant frequency. This is because the precise resonant frequency shift of each nucleus depends on the magnetic field. Instrumentation of NMR. The NMR contains sample tube, magnet controller, detector, RF transmitter, and see 1H1 NMR chemical shift of some compound like this. Spinning nuclear magnetic moment. Now when the nucleus is placed in a magnetic field, what happened? Before the nucleus is without, means when no magnetic field is not applied, see the random motion of the nucleus, while when the magnetic field is applied, they are get aligned to the magnetic field. Now when the magnetic field is applied, two phenomena are observed, that is shielding and de-shielding. The shielding, the higher the electron density around the nucleus, higher the opposing magnetic field to V0 from the electrons, and greater the shielding. Because the proton experience lower external magnetic field, it needs a lower frequency to achieve resonance, and therefore the chemical shifts of field. De-shielding. What happened in de-shielding? If the electron density around the nucleus decreases, the opposing magnetic field becomes small, and therefore the nucleus feels more the external magnetic field B0, and therefore it is said to be de-shielded. Because the proton experiences higher external magnetic field, it needs to have higher frequency to achieve resonance, and therefore the chemical shifts down. The applied magnetic field, the nucleus is shielded and de-shielded higher energy level. The most important is NMR is precession. Precessional motion. As the protons behaving a spinning magnet, it can align its field. So if the induced magnetic field opposes the applied field, then the nuclei in a molecule exert an external force which shields the nucleus from the influence of applied field, and the proton is said to be shielded. If the induced field, what happened? If the induced field reinforces the applied field, the proton feels higher field strength, and thus such a proton is said to be de-shielded, shielding effect, and de-shielding effect when the applied magnetic field is applied now is given in the diagram. High electron density around a nucleus shields, lower electron density around the nucleus shielded. Most important is the coupling constant. The spacing of adjacent lines in the multiplate is a direct measure of spin-spin coupling, and this spin-spin coupling is known as coupling constant. It is denoted by J and expressed in Hertz or cycle per second. It is the most important concept in coupling constant. Before splitting of the nucleus, we must know about equivalent and non-equivalent protons. The protons which are equivalent means present in the same environment gives the same peaks, while the non-equivalent protons gives different peaks or signals in different protons. See 1H1 NMR chemical shift of some compound like this. Spinning nuclear magnetic moment. Now when the nucleus is placed in a magnetic field, what happened? Before the nucleus is without, means when no magnetic field is not applied, see the random motion of the nucleus, while when the magnetic field is applied, they are get aligned to the magnetic. Equivalent protons in alkenes must cease to the same group. Ha and Hb both cease to Br, they are equivalent, 1 NMR signal. While in last one, Ha is ceased to methoxy, while Hb is ceased to Br. They are not equivalent, that's why 2 NMR signal and from A and B, and only one signal from CH3. Some common splitting patterns: splitting for Ha, split structure, and then splitting for Hp. See some common splitting pattern. Now if no coupled hydrogens, then only one singlet. If one coupled hydrogen, then one doublet. Two coupled hydrogens, then doublet of doublet, and three coupled hydrogen, a doublet of doublets is observed in energy level. The most important is NMR is precession. Precessional motion, as the protons behaving a ground field. So if the intense magnetic field opposes the applied field, then the nuclei in a molecule exert an external force which shields the nucleus from the influence of applied field, and the proton is said to be precessional frequency. The precessional frequency of the nucleus is directly proportional to the strength of external field and also depend on the nature of the nuclear magnet. So according to landmark precessional theory, omega equal to gamma H0, where gamma is the gyrometric ratio, equal to intrinsic magnetic dipole moment to spin angular momentum. Now gamma equal to 2 pi v, therefore 2 pi v equal to gamma H0, and therefore V proportional to H0, that is applied. Most important is the coupling constant. The spacing of adjacent lines in the multiplate is a direct measure of spin-spin coupling, and this spin-spin coupling is known as constant. Before splitting of the nucleus, we must know about equivalent and non-equivalent protons. The protons which are equivalent means present in the same environment gives the same peaks, while the non-equivalent protons give. Now this is about some topics related to NMR I have explained here, and thank you.